metal pulsars. Oh, do I have to repeat?
If you want. No.
Okay. All right. It's not moving. It's not moving.
Try click on the. Just click here. Just click. Okay.
Okay. Yeah. All right. So, two fundamental constructions in modern astrophysics. How galaxies formed and evolved, and also how the first stars formed in the universe. How do we answer these questions? We have to go back in time of billions of years. And one way to go back in, yes, this is a very popular illustration of the cosmic history, the universe evolution from the Big Bang until today. And the slides in which I am more interested in is when the first stars formed between 200, 400 million years after the Big Bang. And obviously when the first galaxies formed. So how do we go back in time? First way, we can explore the early universe by looking at very distant objects, high redshift, like, for example, this tiny galaxy observed with ALMA at a redshift of greater than 9, or these beautiful objects recently observed with the JWST with a redshift that goes from 10 to greater than 13. These are amazing objects, but the problem with these objects is that we cannot retrieve a large amount of information, at least with the current technology. So there is another way to go back in time. We can look at dwarf galaxies analogs to the high redshift ones. And this is going to be the topic of my next talk in here, hopefully. And or observe and study ancient stars in the Milky Way, and in particular their chemical composition and the way they move in the galaxies. So where are these stars? Let's have a look at the structure of the Milky Way first, which is a barred spiral galaxy, like this one represented here, or similar to this. Sorry, I could not help myself. I had to show Euclid that. This is one of the early release observation, and you can see the difference with respect to the previous. Anyway, the structure of the galaxy, the main structure in the Milky Way, we got obviously the disk components, thin and thick, and they represented here, central bulge, and then a halo, a stellar halo that surrounds all the other galaxy structures is very extended, much more extended than the rest of the structures. So these ancient stars are in the halo system. The halo is a very important structure for us that perform near-field cosmology because it's old and metal poor. It comprises at least two main components, inner and outer halo, and several substructures and overdensities that can be, some of these structures can be seen only in phase space, and more than 150 globular clusters. Now, when we talk about halo stars, we talk about metal pool stars. And there is a very nice nomenclature. First of all, we talk about stellar metallicity. And these are the category of metal pool stars that we are dealing with when we perform this kind of studies. And I want to point out these stars, in particular, the extremely metal pool stars below -3 that can carry the signatures of the first stars formed in the universe. So we work in this scenario in which the first stars formed in a gas cloud polluted only by the Big Bang nuclear synthesis, hydrogen, helium, some lithium, and they were the modern computational models predict that these stars were massive, short-lived, and they exploded as cold collapse supernovae. So, what kind of stars were they, the first stars? Actually, we don't know. We never said one, in particular, if they all exploded, obviously. But the thing is that there are some models that I'm listing here only some of them that are the one that works better in reproducing the chemical patterns of the most ancient stars in the halo system. The first model is the faint supernova. These stars are massive, with a mass between 10 and 100 solar masses. And what happened in this model, these stars, during the explosion, there is the elements mix. There is a mixture. There is a process called mixing and fallback, and the element can get to the upper layers of the star, the atmosphere, but only the light element can get ejected, and the heavy element fall back in the central forming black hole, like here, the heavy elements are represented by iron. And the reason for that is that this is a failing supernova. It's not energetic enough to eject all the elements, the yields in the interstellar medium. The second model is the spin star, massive spin stars. This is more massive, between 50 and 100 solar masses. And here, in this case, the mixing occurs because it's induced by rotation. Rotate very fast, and so there is this mixture of elements formed, synthesized within the star. And even in this case, when the star explodes as Kolkola supernova, light elements are ejected, a little bit of iron, but not much, obviously, because the metal, otherwise the stars that we observe today, they will be not metal poor. And then this beast here, which has a mass between 140 to 160 solar masses. The pair instability supernovae. These are enormous stars, and the equilibrium in them occur because there are gamma rays. But when the gamma rays decay in positrons and electrons, the star collapses and explodes. There's this enormous explosion, super luminous, and all the elements in this case are ejected in the stellar medium. There is not a preference. It's not clear exactly how we can distinguish the signature of these kind of first stars if they existed. One way is the variance between odd and even atomic number elements like sodium and aluminum. But I will not address this today, only the first two models. So this is the abundance, a diagram that shows the abundances of a star in the halo with metallicity below -5. This circle here, the red one, shows the abundances, the measured in this star, and this black curve shows a faint supernova model with 25 solar masses. As you can see, there is quite a good agreement with some scatters in some cases, but at the moment we are happy with these models. So the scenario is that the first stars formed in this gas cloud, metal-free. Then the second generation stars, population 2 stars born in the gas cloud polluted by these first stars. And these are the stars that are in the halo system and we observe today. Another piece of information that is very useful for us is the way these stars move in the galaxy. The main movement in the galaxy, motion in the galaxies, is the stars can rotate very fast around the center of the galaxies, like these stars, or they can move like this. Halo stars, they move randomly. It's not they move randomly in this way. They don't rotate. They don't have this motion like the motion as these stars is very different. So why the motion of halo stars is so important? Because these stars, remember where they come from. They have a dynamical imprint of the assembly history of the Milky Way. And the reason for that is that in the halo, the time to exchange energy and angular momentum is larger of the age of the galaxy itself. And so they really have this imprint and remember the progenitors where they formed. So it's very well known that this field that I'm addressing today is called near-field cosmology. And we can do this type of studies, chemo-dynamical studies, not only in the Milky Way, but also in the satellite galaxies around the Milky Way, eventually in the local group, if we have good data, enough good data. So quite a few years ago, can you believe it's already 60 years, 46, yeah. So by doing this type of stars and using a sample of SDSS data release 5.7, we found evidence that the halo component could be separated into the halo system could be separated in two components. The inner halo, which is dominant at galactocentric distances less than 10, 15 kiloparsec, shows high eccentric orbits. Basically, on average, does not rotate, and the metallicity peak is at minus 1.6. We now know that this structure is dominated by the Gaia Enceladus debris system, and I'm sure you have heard about this structure, but I will talk more about this later. And the second component is the outer halo, which is dominant at galactocentric distances greater than 15, 20 kdc, shows a more uniform distribution of eccentricities. The metallicity peak is a minus 2.2, so it's very metal poor, and is in high eccentric orbits. So high retrograde orbits. When I talk about prograde retrograde, very important distinction. Prograde stars have the same direction of the galactic rotation. Retrograde stars rotate in the opposite direction. These are the velocity ellipsoids for the components that we have identified. As you can see, the inner halo is basically not rotating. The outer halo has this highly retrograde motion, and the velocity dispersions for the outer halo are much larger with respect to the inner halo. Now, the important thing to know is that before Gaia has released very high accurate astrometric parameters. But before that, we didn't have those parameters, and we only capture the coarse-grained properties of the halo. Now, talking about coarse-grained, before that, these are works, observational works that confirmed the duality of the galactic halo, highlighted in blue, and in green, the theoretical works. Now, in 2021, in collaboration with Masashi Chiba in Japan, we performed the so-called coarse-grained phase-space analysis, where the properties of the halo system is averaged over the phase space. And this differs very much from the fine-grained one, in which basically we have two distribution functions in phase space, the coarse-grained and the fine-grained. The fine-grained distribution function can recognize structures in the halo that are still not relaxed, not well phase space mixed. So, and basically, when we look at the halo with this distribution function, the coarse-grained, is like the system is closer to a dynamical steady-state system, like in equilibrium. So, we using this paper, we have reanalyzed the halo system with this distribution function, large samples of stars, all the calibration stars from SDSS DR7, apogee, and the phase space is defined by the three integrals of motion. LZ, which is the vertical angular momentum, that basically provides measure the rotation of the component in the galaxy. The total energy, E, and the third integral of motion. The potential is the Stekel type gravitational potential. And a few words about I3. The third integral is not easy to determine. Only through numerical techniques computation. But in the Stekel type, we have an analytical form. And the Stekel type gravitational potential has two components, a flattened disk and a massive dark matter halo. Now, the thing is that the Stekel potential is a very good approximation for many of the potential that are used nowadays in many works. Okay, this is the third integral that has the dimension of an angular momentum, basically, kiloparsec, kilometer per second, as a function of Lz, the vertical angular momentum, and this is energy as a function of Lz. Now, if we look at this diagram, from top to bottom, the metallicity decreases. So the gray dots shows the entire sample, and the color-coded dots shows subsamples with different metallicities. As you can see, high metallicity stars, this sample here is a combination of thin and thick disk stars, have a low value of the third integral of motion, and they rotate very fast, as expected for these stars. They are on this part of the parabola shape in the energy versus angular momentum. And as we move down to lower metallicities, we can see that stars progressively goes to lower values of Lz, and this is a combination of the thick disk and metal wick-fit disk. But the important aspect is that when we go at lower metallicity, below -1, these are mostly halo stars. You can see that I3, the third integral, is always greater than 500 kpc, kilometer per second. Here, I highlighted with this ellipse here, the Gaia Enceladus is very easy to recognize these elongated structures here. And when we go at even lower metallicities, here we go below -1.4, -1.8, and this is the very metal poor regime. We have here also extremely metal poor stars. You can see that I3 is always greater than 500 for the metal poor halo. We also noticed a sharp cut in Lz that basically we saw that when we move at lower metallicity, the metal poor halo has no many stars with Lz greater than 1500 kiloparsec, kilometer per second. So basically, what we found in this paper is that we can separate halo stars from these stars, which is not very easy, actually, because there is a strong overlap on an orbit-based selection by using cut in I3 and Lz, because halo stars is characterized by large values of I3. And here, I didn't use 500, but 1,000. Why that? Because the metal wick-fit disk can have orbits that with the larger values of I3. So if we want to remove the metal wick-fit disk, we need to go at larger values of I3. That correspond to an orbital angle greater than 15 and 20 degrees. What is the orbital angle? Basically, during the orbits, this is the angle that the orbit has with respect to galactic plane. And in this case, this is the maximum orbital angle. So and at the same time, if we use this cut and Lz between 0 and 1500, these are basically halo stars. In the retrograde, when Lz is less than 0, and so stars are retrograde, we don't need to perform these cuts because they're all halo stars. These stars, on the contrary, they have large values of Lz greater than 1500 and low value of I3. Large value of Lz, a low value of values of I3, and the lower orbital angles. So the Gaia Enceladus debris structure, and it's very well-known structure. Here, I just want to show this diagram that this is the rotational velocity in the Cartesian reference frame. These are the two other velocity components, a term that depends from this velocity component. Thin disk stars, the dark stars are basically halo stars, and this is the structure. It's a very well-known structure responsible for the formation of the thick disk, occurred 10 gigayears ago, and has been a lot of papers on this structure. But one thing I want to point out is that in this paper, as well as in many other papers, the way astronomers, colleagues, separate disks from halo stars is through the high velocity cut. What does it mean? It means that the total velocity of the star is compared to the velocity of the local standard of rest, and then the absolute values is taken greater than fiducial limits, like, I don't know, 200 kilometers per second, 180, and so on. However, we have to be careful because that cut introduces biases. Indeed, this is the energy versus angular momentum for the vertical angular momentum. For the gray dots is the entire sample of calibration stars, and the orange represent the stars when we apply the high velocity cut. And as you can see, this cut misses a lot of stars with in this area that still belong to the halo. These stars still belong to the halo. On the right, when we use the cut that in orbit-based selection, we don't miss those stars. So, and this is important because we have revisited the dual halo in this paper, and this is the metallicity distribution function for data release 7 SDSS stars, and from values of LZ that goes from slightly prograde, positive values of LZ, and progressively from top to bottom toward retrograde motion. So as you can see, when we have LZ between 500 and minus 500, the MDF is dominated by the inner halo population with a metallicity peak around minus 1.5. And then as we move towards lower, more retrograde motion, the MDF shifts toward lower metallicities, and when LZ is less than minus 1,000 kiloparsec kilometer per second, we have that the MDF is in the very metal poor regime with peak at minus 2.2. So Gaia Enceladus does not dominate the very metal poor halo. So we found in this paper in 2021 that the inner halo includes the debris structure that dominates the component in this metallicity range, and but also contain low energy stars at up to a metallicity of -1 that are missed by the high velocity cuts, and a significant numbers of metal poor progress stars. The outer halo, on the contrary, is dominated by very metal poor stars with predominantly retrograde motion, and we thought that it's likely made of all the structure, many of the structures in phase space that are recognized with the fine-grained phase space analysis, like, for example, this structure here, this one, or the dynamically tagged groups. It can be completely accreted. Now, but the important thing to remember is that the retrograde outer halo is very metal poor. The peak of metallicity is -2.2 toward, and comprises also many stars with the metallicity in the extremely metal poor regime. We also considered the fraction, the number of stars with in the very metal poor regime with metallicity below -2.2, and over the number of stars with larger, higher metallicities in the inner halo region, and as a function of the third integral, and this is the orbital angle. And as you can see, the very metal poor halo dominates at I3 greater than 2000, so very large values of the third integrals that correspond to orbital angles of 50 degrees. So the very metal poor stars that we are interested that are in the halo, obviously, but is the halo only the main locus of these stars. So definitely we can find them in the outer halo. What about the Gaia Enceladus debris system? So, well, the metallicity peak of this structure is -1.5, right? It's not very metal poor. And there is also this paper from Bonifacio. This is basically represents the metallicity, low metallicity tail of the metallicity distribution function for their sample of stars. This is the average halo. And this is the trend for the Gaia Enceladus debris stars they had selected in their sample. And as you can see, there is a sharp drop. It's very steep, this trend, that it means that Gaia Enceladus, yes, got some VMP stars, but is not dominated by them. So where are VMP stars in the galaxies? The halo, the outer halo in particular. But we also found these stars, VMP stars, in the disk. VMP stars in the disk, and there is also a paper from Michele here that I'm mentioning, and one of my papers of last year. So this is a different sample that we used, Hamburg isosurvey sample, and again, the third integral as a function of LZ for very metal poor stars. This is below -2.5. This is the extremely metal poor regime. And this box here shows the region in phase space where the disks are located with LZ greater than 1500 and low values of I3. And as you can see, there are several very metal poor stars in the disk. So we found that also that when we look at the stars in the phase space dominated by the disk, the very metal poor, and we compare with the retrograde counterparts. What does it mean, retrograde counterparts? LZ is less than -1500, and I3 is less than 1000. And we found that in the prograde direction, we got 3 times more stars than in the retrograde counterparts. In agreement with Sestito, one of the paper, but also I think Michele also found similar results. So another sample of stars, group of stars that I am interested in are the very metal poor Moss-bound halo stars. This is the energy versus angular momentum for the Hamburg isosurvey stars. These values of energy has been identified in a 2021 paper. Is for the Stefan potential, is the energy below which we can find the most tightly bound stars, halo stars, tightly bound to the gravitational potential of the Milky Way. I will talk more about these stars later. Now, let's forget for a moment. Let's put aside the motion in the phase space, and let's talk about some chemical signature that I'm really interested in. When we talk about abundances, a chemical signature, it would take 8 talks, really, because it's so complex to talk about all the possible signatures in the halo system. But today I will focus on this particular class of stars, the carbon-enhanced metal poor stars. These are stars, metal poor, and they show a lot of carbon in their atmosphere. So the thing is that the nature is more complicated than we think, as usual. And there are also subgroups of stars, or CMP stars. And the 2 categories that I'm more interested are these, CMPS. What does it mean? They are carbon enhanced, but they also show enhancement in slow neutron capture process elements, like, for example, barium. And the second, the second category I am more interested are the CMP0 stars. These are carbon enhanced, but they don't show the same enhancement in barium. So just a quick word about the neutron capture process element. It's very well known that half of the elements are produced in this type of nuclear reaction, and the slow occurs when the neutron density is low in asymptotic giant branch stars in particular, and the rapid neutron capture elements occur in explosive environment like collapse supernova, where there is high neutron densities. So how these stars got the carbon? This is the question. They are metal poor, and there is this carbon. So for the CMPS progenitors, we are now quite confident, almost confident, that the progenitors is the star basically that we observe today is in a binary system. The primary star is an intermediate mass, has an intermediate mass between these values here. And during the AGB, many elements, light elements, get to the upper layers of the stars during the third dredge up. And of course, there is carbon, oxygen, and the products of the slow neutron capture, like barium. Then through the mass transfer, the secondary star get polluted by these elements, and we observe this star today. There has been a monitoring of radial velocities, long-term programs, and we now know that these 85% of the CMPS stars are in binary systems. So this is a very, we are pretty confident with that model. But what about the CMP0? How did I get the carbon? The answer is that we don't know. There are hypotheses. The CMP0 stars, they lack neutron capture element overabundances, and they basically, we think, form from a gas cloud polluted by the first stars, population-free stars. And I talked already about these models earlier. And but again, nature is more complicated, unfortunately. And so if we look instead of the carbon over iron abundance, we look at the absolute abundance, which is carbon over hydrogen. We have this, we found out in this paper, this diagram, which is the absolute carbon abundance as a function of the metallicity for a large sample of stars for which we had the high resolution spectroscopy available. So we have been able to find, we know the barium abundance. These are CMPS stars, group 1, CMP no stars in red. Also, these are CMP no stars. As you can see, there are two plateaus in AC. The higher plateaus where they sit the group 1, CMPS, and the lower plateau where they sit the group 2. Now, the fact that the CMP0 has behaved in this way in this diagram, have two different trends, means that they also had likely different progenitors. I mean, they got the carbon in an intrinsic way because they formed in these gas clouds polluted by the first generation of stars. But maybe the group 2, the progenitors were faint mixing and fallback supernovae, while the group 3 spin stars model. Or there is something else that we still don't know. We haven't found a possible cause of progenitors for these stars. Obviously, well, I'm working on that at the moment with a large sample of stars with high resolution spectroscopy. When I will have the results, I'm happy to talk about this. But I'm just showing here what we got in the past. Looking at the CMP stars in the inner outer halo, we found that the outer halo has a number of CMP stars twice with respect to the inner halo. And when we look at the distribution in the inner outer halo of CMPS and CMP0, in this work, we found out that the inner halo has a number of CMPS, which is twice the number of CMP0. And the opposite happens for the outer halo. The number of CMP0 is twice the number of CMPS. This has an implication, strong implication that I will talk in a minute, in 5 minutes. Now, let's have a look at a little bit of storytellers of galaxy formation from this result. Obviously, we work in the hierarchical structure formation of galaxies, which is nowadays a generic feature in lambda CDM. The composition of the universe is mostly dark energy, a significant fraction of dark matter, and a tiny fraction of atoms. So what we said in the past, the formation of the fact that, let's not forget that I'm talking here about the global properties of the halo in the average over the phase space. So we said that because the inner outer halo had such a different properties, chemo-dynamical properties, they form in a totally different way. And what we say is that the inner halo formed through a dissipative merger of few massive subgalactic fragments, or let's say satellite galaxies. These galaxies have a large amount of gas in them, sustained star formation, and is dissipative because they got such a large amount of gas. And Gaia Enceladus is one of these dissipative mergers, that likely the last one that occurred 10 gigayears ago. And the outer halo, on the contrary, was formed through a dissipationless, chaotic merging of small subsystems within the dark matter halo. Why is dissipationless? Because these are tiny mini halos. They have not enough, a lot of gas in them. And likely when they interacted, merged with the parent galaxy, they got tidally disrupted. And, or if they survive today, we can observe them as ultra-faint asteroidal galaxies around the Milky Way, satellite of the Milky Way. This is a very cute simulation about what I just have said, the formation of two big clumps in this simulation. They merge and grow, and then the chaotic merging of small mass subgalactic fragment later on. So let's talk about a very popular topic. I got how much? Sorry. It's good. Very popular topic these days, in situ inactive stars and in the halo, or anyway, in the galaxy in general. But let's talk about the halo. So what are in situ stars? We look at the theoretical prediction and suggest that these stars, in situ stars form within the parent halo during the formation of the galaxy, within the virial radius. Now, if we consider the early stages of galaxy formation, and we got these dark halos, mini halos, they grow, they merge and grow, and the stellar components within these dark halos have multiple sources. Stars can form within cool gas that was originally present in the parent halo, and so therefore these stars, obviously, they are in situ. They can form from gas stripped from merging satellites and subsequently cooled, or they can stars can form in satellite galaxies, let's say mini halo, and then they merge in the parent halo, and these stars go accreted to the main galaxy. Now, so we have this scenario, we have these halos, the main parent halo, and these halos grow and merge and grows, and within these merging halos, the product of the merging, the stellar components, are formed by pre-existing stars within the main progenitor halos, and therefore they are in situ stars, or stars coming from other halos, therefore they are merged in therefore they are accreted. So now let's consider the parent halo and the stars formed within this parent halo at the very early stages of galaxy formation. And we got these stars formed from the cooled gas. A finite fraction of these stars formed at the bottom of the main progenitor halos. These stars are most tightly bound to the gravitational potential of that halo after dissipative cooling. In comparison, if we look at consider the accreted subhalo that merge, these stars have larger energy with respect the one that are inside the parent halo. So therefore, we can consider candidate in situ stars can be defined those as being most tightly bound to the Milky Way gravitational potentials. And, or in other words, those that have the lowest binding energy. This is why I am so interested in these most bound stars in surveys. What about the stars, the VMP stars in the disk? How did they get there? How did they form there? Consider that I'm talking here about very metal poor and extremely metal poor stars. So the one that we found in the Hamburg-Giza survey. What we think is that if we have the parent halo, the early stages of galaxy formation, and there is an initial angular momentum, then a pristine gas could have settled there, and stars form from this pristine gas in the presence of angular momentum. And so the star, maybe the stars that we observe today in the disk formed from this pristine gas, and they were just left there. And so, and obviously they are in situ stars. Just a quick comparison with simulation to test these ideas. We looked at high resolution hydrodynamical simulations, Aquarius C, and Elastis TNG Galaxies, TNG 50. And in both simulations, we follow back in time in the merger trees, the star particles, and we look at the system where they form, the time of formation. There is a lot to say about this comparison to simulation, but here I just want to tell you what we found. This table is in my paper. Anyway, these are two ranges of metallicity, the rotation, these kinematics, retrograde counterparts, the origin in situ accreted, Aquarius Cs, and the four Milky Way analogs selected from TNG 50. And what we found is that the very metal stars with these dynamics, they are both accreted, they were formed both accreted and in situ. But there is a systematic larger contribution of accreted stars. But this is also important that some of these stars formed in situ. And the other very nice result is that these stars are very old in this simulation, 12.5 gigayears, corresponding to this redshift. And this is consistent with the claim that they formed during the very early stages of galaxy formation. And what is interesting is that we look at if you look at this paper, very interesting papers, in the extragalactic domain, these colleagues here have found gaseous disks in star-forming galaxies at high redshift. This is the redshift corresponding to this age that is consistent with what we found in our simulation. So what about the most bound halo stars? The same table as before, both mechanisms of formation in situ and accreted are also valid for the most bound halo stars. The interesting characteristic is also that these stars are the oldest detected in this simulation, with an age of 13.3 gigayears. And so what the message that I want to say is that we want to look at candidate, we want to find candidate in situ stars, we had to look at the VMP stars with these dynamics, and also the one that are most bound to the gravitational potential of the Milky Way. And this is what I'm doing also at the moment. I'm gathering high resolution spectroscopy, and it's not ready yet. So another talk, and I will show those results. Now, quickly, the fact, the CMP distribution in the inner outer halo, we saw before that CMPS formed in a binary system. CMP know the origin is likely the first stars formed in the universe. So let's consider these scenarios then. And we saw that the CMPS predominate in the inner halo, the CMP know predominate in the outer halo. And because the CMPS and CMP0 phenomena vary with the mass of the progenitors, there is a link to the initial mass function. And what we say is that if this is the parent primordial galaxy, and this is a big subgalactic fragment, the one with a lot of gas, sustained star formations, higher metallicity, so the initial mass function must be steeper, because it has to accommodate a larger numbers of intermediate mass stars. On the contrary, the small mass subgalactic fragment that merge with the parent galaxy, they have a flatter IMF because they have to accommodate massive stars, the first stars. And so we did this calculation in the past paper, and we went with the salpeter IMF, the slope changes from this value to this value. But something that I wanted to also say is that in a recent studies using HST data from some study, most of the study, ultra-faint spheroidals around the Milky Way, it has been found some confirmation, a trend that the IMF may be shallower in these ultra-faint spheroidals. But in agreement with what I just have said, but of course, more confirmation and theoretical works are needed. And I think I leave you with this summary of the implication for galaxy formation. And I really thank you very much for your attention.
Daniela, questions?
Of course.
I've got many.
I know.
I try to speak with
okay,
a couple.
kill me.
No, not at all. So one question is on the selection with I3.
Yes.
So my impression is that I agree with you that using I3, the selection is more complete in terms of the halo, but maybe it's less pure. And so I wanted to ask you if you have an estimate for the purity whenever.
What do you think less pure? With respect what less?
There is also a question that I wanted to ask you. It depends on what we define as halo, no? So if with halo we mean accreted stars, then what I think as not pure is all of the disk that is being heated up and would end up in your selection with I3, that would less be included in the selection with the velocity, for example.
First of all, the halo is not purely accreted. It's not. There are situ stars formed in the halo, and mainly the outer halo is purely accreted. But when we use the I3, when we do that selection, we at higher values of I3, we also select stars with LZ less than that sharp boundary. So this is why we think that we believe that these stars, in particular, the heated stars, are not there because obviously some contamination. There is some contamination, and we can go a little bit upper, like 1,000 and 100, for example, and so to have more purity.
Yeah, that was my question.
Yeah.
It's always now a trade-off.
Yeah.
If you
Yeah.
go for the extreme rate, you are sure that you are sampling pure halo population, but you're missing something. If you
But
try
if-
to include everything,
Yeah.
you are at more contamination. There is no way to avoid this.
Yeah, some contamination is there,
Mm.
but in particular for the metal liquid disk, I have no time to show you the metal liquid disk, which is another talk. Is basically is a structure that has a lower rotation with respect to the main component, the main disk components, and has a metallicity, lower metallicity as well, -1. So this is interesting because the metallicity disk has also high values of I3, can reach higher values. And this is why we did a dead cut of 1,000 in I3 to just remove the metallicity disk. In the paper, there is an analysis on that. But it's interesting to see, now we know very well about the inner halo, and not all the inner halo is accretive. The part where the metallicity peak is at -1.5, yes, is Gaia Enceladus, right? But as I showed earlier, the inner halo has also other stars in the halo that can form as a situ star.
No, yes, another question, Krishna, is also that, again, my impression is that in the spaces with I3, the halo looks smoother. Is that so?
Okay, we use here the coarse-grained distribution function. We didn't use any clustering technique. If we do that, we are going to see structures,
Okay.
but we didn't use the fine-grained distribution function. That makes sense? We
When
didn't.
you get I3 from without using the distribution function, you get I3 from assuming a stack of potential and finding the ground.
No, but I
So
said,
by only
yeah.
by only looking at the spaces, I would have said that the distribution of stars looks smoother. But maybe I'm wrong. Maybe I wanted to know if you were to select Sequoia or whichever you wish and plot it in the spaces with I3, would they be still clusters or not?
Again, if you want to disentangle phase structures that phase cluster because they share common kinematics, we need to you can see if you plot your star, whatever you're looking, this type of plot, you don't recognize quickly the structure. Gaia Enceladus, yes.
Yeah,
Because it has this elongated
Yeah.
distribution, but Sequoia is in there, in that retrograde part of the halo. In order to recognize them, you still have to do some clustering analysis because if you know I3, it's not I3. And but we consider also that here we didn't do any type of that clustering.
Yeah, sure. Yes,
We just consider the global properties of the halo. Sequoia is in there, in those plots, but we didn't disentangle these.
Based on your analysis, is it safe to conclude that the majority of the stars in the disk formed in situ?
Well, I'm talking here about the very metal pool regime. I'm not discussing the thick, thin disk. The very metal pool, no, the majority is not formed in situ at all. We saw them we saw it in the simulation that the majority actually are critical. And but there is also
Of the metal pool.
the metal pool, yes.
You are
Yeah.
talking about probably 1% of the
Right.
No,
of the
actually,
disky If you consider the entire disk.
Oh, different, yeah. Sure.
Like
Yeah,
a component of very,
yeah.
Another question, so a curiosity that I always had concerning the halo. So, leaving alone the roller cluster, is the density profile, density structure of the halo known? So is the halo like a homogeneous sphere?
It's a break radius. The density profile breaks at 20, 25 kilopascal.
So how can the profile be modeled by a like a power?
This is what we saw, some colleagues saw in the papers. I didn't do this analysis now.
a broken power law.
Yeah.
Yes, there is a
With
broken.
different aspects.
With a characteristic, let's say, length.
That is about 20 kbc.
25 kbc. In some works, they go even further, like 30, 35, but look.
Okay.
There is a broken power law, yes.
And do the simulation that you have analyzed and considered, can the simulations account for the basic, let's say, structural parameters of the halo?
Yeah.
In general?
Yes, of course. There are some paper, some of the theoretical papers I showed earlier, Patricia Tisera, I told, 2013, 2014, she made an analysis, they made an analysis. Actually, I was in those papers. We made an analysis where all the structural parameters were also present. And the chemo-dynamical analysis, and we saw we separated the inner outer halo using the binding energy in those cases, and we also looked at the trend as a function of the galactic distance, and we looked at all the structural parameters of inner outer halo. But not this, not
And
this.
did you find a barrack in their halo profile in simulated galaxies?
We do see that.
Okay,
We do.
thanks.
Other questions? There is something from, okay, so it's not we.
He works on AGN.
So we thank again Daniela, that is downstairs in the also office, if someone wants.
So it's a student. Com'era? L'ho spiegata bene.